symmetric and anti-symmetric. We are going to use boundary conditions. Okay, now we are going to use boundary conditions. What is the meaning of boundary conditions? It says that the wave function at this boundary is continuous. That is phi 1 which is equal to phi 2 at the boundary. Wave function is continuous. And also derivative of the wave function also is continuous. You are going to take the differentiating psi. So d psi with respect to x, that also will be continuous. So there are two boundary conditions. One is phi is phi in the first region to the second region with the boundary also is continuous. Also its derivation also it will be continuous. Okay. So two things are there. So now this is the boundary. Okay. So either you can apply this condition, that is phi 1 equals phi 2 at x equal to minus a by 2, or otherwise phi 2 with phi 3 at x equal to a by 2. So either way you can do it. You will get the same answer. For the simplicity, we are going to take this region to this region, that is phi 2 to phi 3. Here at x equal to a by 2, the wave is continuous. It means that this wave will go to that wave. Okay, that region. So phi 2 in the second region at x equal to a by 2, which is equal to phi 3 in the region 3 at x equal to a by 2. So this is another. Now when you differentiate, that will give you d phi 2 by dx at x equal to a by 2, which is equal to d phi 3 by dx at x equal to a by 2. So now you are going to have these two boundary conditions. First we will go for the symmetric solution. Okay. So B symmetric solution is nothing but you are going to substitute now. Instead of x, you are going to substitute a by 2. B cos k2x, which is equal to, this is in the region 3, correct? De power minus k2x. Instead of x, you are going to substitute a by 2. Clear? Here, see, this is region 2, this is region 3. We are going to equate these two. Okay, we are going to equate these two. Phi 2 equals phi 3 at x equal to a by 2. So b cos k2 instead of x, you are going to write a by 2, which is equal to de power minus k1 a by 2. Now you differentiate to go for the second boundary condition. You differentiate. So that will give you minus b cos k2 sin k2 a by 2. Okay, cos, that will give you minus sign. So when you are going to differentiate, this one will be minus d k1 e power minus k1 a by 2. Okay, this minus will go off, or otherwise we can divide. So divide this by this, that will give you minus will go off. So dividing this by this, that will give you sin by cos will be tan, and b will get cancelled. You have k2 and d gets cancelled. This term also will get cancelled. You have k1. So k2 tan k2 a by 2 equals k1. Okay, here k2 a by 2 is there. Okay, correct. Here we have k2 a by 2. So I am going to multiply on both sides by a by 2. So to make it equal. Okay, so I am going to multiply on both sides by here a by 2. Here also a by 2. So that will be your k2 a by 2 tan k2 a by 2, which is equal to k1 a by 2. So it will be uniform. Okay, to simplify again, this equation is known as transcendental equation. It means that you are going to substitute some values so that the answer should be equal on both sides. Any equation which cannot be solved, this equation cannot be solved. How you are going to solve? We can solve only numerically. So this can be solved numerically. That is, you substitute the value for k1, you substitute the value for k2, so that you will have to find out for which values these two expressions are equal. Only then you can get the solution. So this type of equations are called transcendental equation. Is it clear? You are going to substitute one value for k1, you substitute for one value for k2. You just find out both the answers are the same. That answer is nothing but for k1 and k2. Okay, so those equations are called transcendental equations. Okay, so as I said now, a by 2, so k2 a by 2, multiply on both sides by a by 2, that will give you tan k2 a by 2, which is equal to k1 a by 2. We will keep this term as xi. Okay, this is xi. Okay, not psi, it is xi. So xi, tan xi, we are going to keep this as eta. Okay, xi tan xi, which is equal to eta. This is also a transcendental equation. Okay, your xi will be k2a by 2 and eta will be k1a by 2. And xi and eta, they both depend on energy. Okay, because k depends on energy, k1 depends on energy, k2 depends on energy. K we have written in terms of xi and eta, so both depend on energy. So we are going to find out now xi and eta. We are going to substitute k2, we will get the energy value. So this is the idea. Okay, now you add these two, that is xi squared plus eta squared. So xi squared plus eta squared. The expression for xi squared is nothing but this one, eta squared is this one. And of course your k1 squared equal to this one, k2 squared equal to 2me by h bar squared. You substitute in this expression. So we have k2 squared, correct? k2 squared equal to 2me by h bar squared. 2me by h bar squared into a squared by 4 plus your k1 squared will be 2m by h bar squared v dot minus e a squared by 4. This e and this minus e will get cancelled. There exists only 2m v naught by h bar squared a squared by 4. Clear? I repeat, this term and minus e will get cancelled. Okay, you just separate these two, minus e term and plus e term will get cancelled. You will get only 2m v naught by h bar squared a squared by 4, which I have written here. So it's a constant and we are going to substitute all the values. Okay, we are going to assume all the values and this term is termed as r squared. So we are going to have this as r squared. So xi squared plus eta squared equals r squared. Again it's a transcendental equation. Okay, so we are going to solve this equation either graphically or numerically. So numerically we can do, doesn't matter. If we have a computer we can do. Graphically easily we can solve. We are going to solve now graphically. Okay, so this is the final answer, xi squared plus eta squared equal to r squared. So this is for the symmetric solution. Now we will go for the antisymmetric. So what is the condition for antisymmetric? So this is the condition, equation 2.40. So we have taken the antisymmetric solution from region 2 and we have equated to region 3. So minus is there, plus 1 for region 1, region 3 will go for minus. So out of this one we have taken only antisymmetric solution. Just to differentiate, you will get ck2 cos k2 a by 2 minus d k1 e power minus k1 a by 2. So again as usual, you are going to divide this by this, that will give you, we are going to divide this by this, similar terms will get cancelled. You can get minus k2 cot k2 a by 2 which is equal to k1. Okay, so multiply on both sides by again a by 2, that will give you, that can be simplified like this as usual, which we have seen earlier, and this term as xi. So xi cot psi, this minus and I have brought it here, minus eta. Again this is a transcendental equation which cannot be solved. Okay, so we will have to give some suitable values for both xi and eta and equate. Okay, and we will get some values. Transcendental equation. So this is one transcendental equation which we have seen earlier for the symmetric solution, and this is another one for antisymmetric solutions. Now we have two things, symmetric solution and antisymmetric solution. Now we just take this one, when eta equal to 0, you just consider eta equal to 0. So this becomes xi tan xi equal to 0 for all values of 0, pi, 2 pi. Okay, similarly when eta equals infinity, for all the values of pi by 2, because tan pi by 2, tan 90 is infinity, tan 3 pi by 2, that also infinity. So these conditions will be satisfied for this equation. So we know already, just remember this one, we are going to look into. So this is the graphical idea, this graphical solution for symmetric and antisymmetric. Okay, so we have seen three things. Can you remember? Xi squared plus eta squared equal to r squared. Xi is one term, eta is another term, r is another term. What is the equation for any sphere? X squared plus y squared equals r squared. You just remember this one, xi squared plus eta squared equal to r squared. So r is the radius of the sphere. Okay, is it clear? So x squared plus y squared equal to r squared. So similarly, we are going to draw the graph for xi and eta for with r squared as a radius. So this will give you your radius r equal to 1. Okay, so this is, I have taken only the quadrant. I have extracted all the other things. Okay, so this is your first sphere and this will be your second sphere. This is your third sphere and goes on. Now we will have symmetric and anti-symmetric solution as I said earlier. One is tan psi, another one is cot. Okay, cot psi. See, you just look at the turn equation. Turn equation will be infinity at pi by 2, correct? Just now we are discussing about pi by 2. So infinity at pi by 2 and tan 0 is 0, so it will be like this. Your turn curve will be like this. Okay? And look at the scales in the axis. 0, pi by 2, pi, 3 pi by 2, 2 pi. Here also pi by 2, pi, 3 pi by 2, 2 pi. So this is your turn. This is your symmetric solution. Turn curve. Your turn curve will be exactly like this, correct? Your cot curve will be like this. This will go into pi by 2. Cot pi by 2 is 0. So this will go like this. And again you have symmetric solution. This will be like this. And you have anti-symmetric solution. So this is for the symmetric solution. All the solid lines for the symmetric solution. All the dotted lines are dashed lines for the anti-symmetric solution. So this is for xi tan psi eta and this is for xi cot psi equals minus eta. So this is. Now what are the solutions? Psi squared plus eta squared equal to r squared. Okay. We have a circle. So the solution will be where the circle cuts the curve. So that will be the solution. Psi squared plus eta squared equal to r squared. Where the circle cuts the symmetric solution. For example, it cuts here somewhere. So it intersects. So this is the solution. Okay. For the first cycle, see this is the first circle. R equal to 1. N equal to 1. So this is the first one. So we have a symmetric solution or anti-symmetric solution? Symmetric solution because this is only symmetric line. So we have only one symmetric solution. Look at the next curve. Next R, that is R equal to 2. So it intersects both symmetric as well anti-symmetric. So for symmetric we have one, anti-symmetric we have one solution. For the next R equal to 3, it cuts all the three lines, three curves. So this is symmetric, anti-symmetric, and this will be symmetric. So we'll have two symmetric solution and one anti-symmetric solution. It goes on. So this is the way that we can find the symmetric solution and anti-symmetric solution graphically easily. So this is the idea. Okay, as R goes on, R equals n, 2, 3 goes on, the symmetric solution also increases. So here it is 1, here it is 2, here it is 3, here it is 1, here it is 2, here it will be, so it goes on. Okay, it goes on increasing. So at R equal to 1 we have one symmetric value, circle in the diagram. R equal to 2 we have one symmetric value and one anti-symmetric. R equal to 4, the next one, two symmetric solutions will have one anti-symmetric. So as R, for larger R, the more symmetric and anti-symmetric solutions will be there. So they are all discrete values. So solution depends on R. R, solution depends on R. It depends on V0, correct? It depends on V0. Because 2m V0 A squared by h bar squared equals R squared. So solution depends on R, it depends on V0. So it's given like this. The product V0 A squared is nothing but the measure of the strength of the potential which binds the particle to the well. Okay, so this is the idea. Now deeper and broaden the well. So broaden well and deeper well, the larger well is of R, hence the larger bound states. In general, the well width at which state n is allowed is given by R equals n pi by 2. Similar relation also we will have xi equals n pi by 2. When v tends to infinity, R also will become infinity. When xi tends to infinity, this condition will be satisfied, 2n plus 1 pi by 2. When cot psi tends to infinity, this condition will be satisfied, psi equal to n pi. So put together, that will give you xi equals n pi by 2, n equals 1, 2, 3. It is not 0, it is 1, 2, 3. If it is 0, there exists no wave function. So it has to start only with 1. So squaring, just square it, that will give you xi squared equals n squared pi squared by 4. Xi is connected with k1 or k2 or k3. Xi is connected with k2. So k2 is nothing but 2me by h bar squared. Okay. So you have 2me by h bar squared a squared by 4, which is equal to n squared pi squared by 4. So simplifying, that will give you En equals n squared pi squared h bar squared divided by 2m a squared. So this is the expression for the energy eigenvalue for an infinite quantum which we studied in the last class. Okay. So this is same. If V0 is very large, so finite quantum will become infinite quantum line. The expression is the same. So the solution that we have obtained for finite quantum is exactly matches with the expression for the infinite quantum well. The wave function for the quantum well in the symmetric case is given by this one. So energy is over now. Our concentration is to find out the wave function now. We have finished the energy E. Now wave function. Wave function is given by, for the symmetric solution, b cos k2x, where k2 equal to root of 2me by h bar square. And of course k2 equals, we can write n pi by a. Can you remember this expression, n pi by l, which we studied in the last class, by n pi by a? How you have written 2mb by h bar square multiplied by the expression for e, just to substitute and get the value. That is, take it out 2m h bar square, you will get n square pi square by a square. Take the root, that will give you n pi by a. So instead of k2 you can write n pi by a. Okay, now we have to find out the normalization constant, as usual we have done in the last class. So physically acceptable wave functions, the energy exists for each quantum number and they are discrete in nature. Okay, quantized. Now we are going to get the value for B. Okay, so now behavior of the wave function in the quantum value, just to analyze. So this is for symmetric wave function, this is for anti-symmetric. Symmetric wave function cos. Okay, this is an even function or odd function? Even function. Okay, even function. So even function is exactly, you just keep it at the center, it must be symmetric on both sides. So this is odd function, so we can't separate. Here we can separate easily. Okay, now we will have to find out now B. For that we will have to use normalization constant. Normalization constant, which is nothing but, we have the expression mod phi n square dx equal to 1. So we know already. So which is equal to 1. We know already. So we have the equation. This equation, just now we saw this equation. Okay, we just square it. That will be b squared cos squared n pi x by a dx within the region minus a by 2 to plus a by 2. That only the well width of the quantum well, which we have assumed earlier. So b squared. So what is that? B squared I have pulled out. Okay, cos squared n pi x. So I have simplified as 1 plus cos 2x by 2. So 2x by 2. I have pulled 2 out. So this becomes 1 plus cos 2x by 2 I have pulled out. Okay. So I have separated 1. I have separated as a dx plus integration minus a by 2 plus a by 2. This cos term. I am going to integrate separately. So dx, that will give me x. Okay. X with the limit minus a by 2 plus a by 2. And this term, cos term, after the integration, you will get in terms of sine. Okay, this term, that is, you will get sine 2n pi x by a divided by 2n pi by a. So a divided by 2n pi by a multiplied by sine this term. You just substitute a by 2 here. Substitute a by 2. So a by 2, 2 gets cancelled, a cancelled, sine n pi 0. Similarly, minus a by 2, you will get again minus sign, that also will be 0. So this second term, simply we can say this is 0. Look at the first term. X, you will have to substitute upper limit and lower limit with a minus sign again. So you will get b squared a by 2, which is equal to 1. So your b will be root of 2 by a. So substitute in this expression, you will get your normalized wave function for the symmetric solution. Okay. Similarly, you can go for the anti-symmetric solution also. So this is your normalization constant. Now look at this figure. So you have a symmetric solution, correct? So these are all wave functions. This is for the ground state, this is for the excited state. First one, second one goes on. And the squaring that will give you probability density function is just a square that will give you CR. And look at, you just compare this figure into the previous figure, infinite quantum well, impenetrable reflecting walls. See, it has come out. So there's a leak. See, it has come out. Your wave function, see, it has leaked. There it is. Because it's an impenetrable barrier. It's a very important differentiation. Okay, you can differentiate this figure into that figure, infinite quantum well. So here also it leaks out. See, the tail comes out. And these are all your squaring of the wave function, probability density function. So normalized one, and that will be your probability density. Okay. So any doubt on the figures? Okay. Now we will solve one problem. That is the end of the slide. So calculate the expectation values of position and momentum of the particle trapped in 1D box. So this is what we solved in the previous one. Okay, this is a similar problem which we solved for the infinite quantum well. So this is for the finite quantum well. Okay, so we are going to use symmetric solution only. So we are going to find out the expectation value of the position where the particle will be found more. Okay, so expression value is given by x sandwiched between complex wave function and ordinary wave function. That is, where x operates on phi x multiplied by its complex conjugate and integrate it, that will give you your expectation value. So now, what is phi n? Phi n is given by this expression. So phi n star will be the same thing, cos n pi x by a, x is here, again cos n pi x by a. Okay, and cos that will give you cos squared. So x into cos squared 2n pi x by a dx. And you have root of 2 by a multiplied by root of 2 by a, that will give you 2 by a. So you have 2 divided by, here x cos square 2n pi x by a. Again we will have to separate using this formula 1 plus cos 2x by 2. So I have pulled these 2 out. So that will give us 2 divided by 2a. Is it okay? So you have cos square 2n pi x by a can be written in terms of 1 plus cos 2x by 2. Okay, multiply with x, that will give you this term. Multiply x with x will give you the second term. So you have x dx. The integration goes from minus a by 2 plus a by 2. This is the first term, and this will be your second term. As usual, we are going to solve this one. We will try. So we will just consider this as u. We will consider this as dv. What is the formula that we are going to use? U dv equals uv minus vd. Okay. So this is u, and if this is dv, what is the value will be your v? It will be in terms of sine. Correct? It will be in terms of sine. You substitute again a by 2 limit minus a by 2, you will get 0. Okay. So uv, the term also will be 0. Again, if you substitute v limit, that also will be 0. So entire terms will be 0. So this term, second term will become 0. The first term alone exists. So you have 2 gets cancelled. You have 1 by a, x squared by 2 plus 0. So answer will be, you substitute, answer will be 0. The position at the point origin, that is 0 is at the origin. See, your well width is minus a by 2 plus a by 2. Your origin is somewhere here, correct? At the position. So main position somewhere lies here. At the main position it is 0. That means at 0 position the expression value is maximum here. That's maximum. The position, it refers the position. Okay. The expectation value of the position lies at 0. Lies at 0. That's the maximum value of finding the particle. Okay. Similarly, just to calculate the momentum. So 2 questions were asked, only position and the momentum. We calculate the position at 0. Minus a by 2 plus a by 2 and the position at 0. We have calculated. Similarly, we calculate the expression value of the momentum for a particle trapped in a 1D box. That will be your assignment. So answer will exist or not? There will be answer or 0. The position, the momentum. We are talking about momentum. So position exists. So answer will be, you just try, answer will be 0. What you say is correct. So because position value exists, so it try. The expectation value of the position lies at the center of the well. At the center of the well, position exists. Okay. So momentum will be 0. So to satisfy uncertainty relation, the average position of the particle is at the middle of the box in all quantum states, and this is for only for the symmetric solution. So we have done only for the symmetric solution. Okay. So that is the end of the class. So in this class, we looked into the description of quantum wells. Okay. Then we have applied boundary conditions. We have used Schrödinger equation, and we solved, and we got the energy values as well eigenfunctions. And one is symmetric solution, another one is anti-solution, and we have solved one problem also. So related to that. Thank you, students. We'll see you in the next class.